Ever felt lost in a web of nodes and edges? Most technical interviews for top-tier companies hinge on your ability to navigate complex graph problems efficiently. In this video, we will cover graph algorithms, practice questions, and explanations for DSA interviews. Master graph algorithms with this comprehensive practice set. In this video, we dive deep into 30 high-impact graph algorithm questions, covering everything from basic traversals like BFS and DFS to complex shortest paths and minimum spanning trees. Grab a pen and paper, and let's see how many of these 30 challenges you can solve. Which data structure is typically used to implement breadth-first search, BFS? Option A, stack. Option B, queue. Option C, priority queue. Option D, hash map. The correct answer is B. Breadth-first search. BFS explores the neighbor nodes first, before moving to the next level neighbors. To maintain this level order exploration, a first in first out FIFO data structure is required. A queue ensures that nodes are processed in the exact order they were discovered, which is essential for finding the shortest path in an unweighted graph. Which search algorithm uses a stack or recursion to explore as far as possible along each branch before backtracking? Option A, breadth-first search. Option B, Dijkstra's algorithm. Option C, depth-first search. Option D, Kruskal's algorithm. The correct answer is C. Depth-first search. DFS follows a last in first out LIFO pattern. By using a stack, or the implicit call stack in recursion, the algorithm dives deep into a graph's branches. It only backtracks when it reaches a node with no unvisited neighbors. This makes it ideal for tasks like topological sorting or finding strongly connected components. In a directed graph, the presence of which type of edge during a DFS traversal indicates a cycle? Option A, tree edge. Option B, forward edge. Option C, cross edge. Option D, back edge. The correct answer is D. During a DFS traversal, a back edge connects a vertex to one of its ancestors in the DFS tree. If you encounter an edge $U, V, where $V is currently in the recursion stack, an ancestor, it means there is a path from $V to $U and now an edge from $U to $V, forming a cycle. Tree, forward, and cross edges do not signify cycles in directed graphs. What is the primary reason Dijkstra's algorithm may fail on a graph? Option A, the graph is directed. Option B, the graph contains negative weight edges. Option C, the graph is disconnected. Option D, the graph has cycles. The correct answer is B. Dijkstra's algorithm is a greedy algorithm that assumes once a shortest path to a node is found, it will not be improved. Negative weight edges break this assumption because a longer path of edges could technically result in a smaller total weight if one of those edges is negative. For graphs with negative weights, the Bellman-Ford algorithm is required. Which algorithm for finding the minimum spanning tree, MST, grows the tree by adding the cheapest edge that connects a vertex in the tree to a vertex outside the tree? Option A, Kruskal's algorithm. Option B, Prim's algorithm. Option C, Floyd-Warshall algorithm. Option D, Bellman-Ford algorithm. The correct answer is B. Prim's algorithm starts from a single node and greedily expands the spanning tree by choosing the minimum weight edge that connects a visited node to an unvisited node. This contrasts with Kruskal's, which picks the absolute minimum weight edges from the entire graph, provided they don't form a cycle, regardless of whether they are connected to the current growth point. Topological sorting can only be performed on which type of graph? Option A, undirected graph. Option B, directed acyclic graph. DAG. Option C, complete graph. Option D, bipartite graph. The correct answer is B. A topological sort is a linear ordering of vertices such that for every directed edge $U, V, vertex $U comes before $V. If the graph has a cycle, no such ordering exists. Therefore, the graph must be directed and acyclic. DAG. It is widely used in scheduling tasks with dependencies. Which graph representation is more space efficient for a sparse graph with $V vertices and $E edges? Option A, adjacency matrix. Option B, adjacency list. Option C, incidence matrix. Option D, edge list. The correct answer is B. An adjacency matrix requires $O, V squared, $space regardless of the number of edges. An adjacency list requires $O, V plus E, $space. In a sparse graph where $E is much less than $V$2, the adjacency list is significantly more efficient. The adjacency matrix is usually preferred only for very dense graphs where $E approaches $V$2. What is the time complexity of the Floyd-Warshall algorithm? Option A, $O, V plus E, $. Option B, $O, E, log V, $. Option C, $O, V squared, $. Option D, $O, V cubed, $. The correct answer is D. The Floyd-Warshall algorithm uses dynamic programming to find shortest paths between all pairs of vertices. It consists of 3 nested loops, each iterating over the $V$ vertices. This results in a time complexity of $O, V cubed, $. While slow for large graphs, it is simple to implement and handles negative weights, but not negative cycles. Which algorithm is most suitable for finding the shortest path in a graph where edge weights represent probabilities, product of weights, rather than sums? Option A, BFS. Option B, modified Dijkstra using logarithms. Option C, Prim's algorithm. Option D, Kruskal's algorithm. The correct answer is B. When dealing with probabilities, we want to maximize the product of weights. Since $log A CDOTB equals log A plus log B $, we can transform the product problem into a summation problem by taking the negative logarithm of the weights. Once transformed, Dijkstra's algorithm can find the shortest, most probable path. Which data structure is essential for the efficient implementation of Kruskal's algorithm? Option A, Fibonacci heap. Option B, disjoint set union, DSU. Option C, segment tree. Option D, binary search tree. The correct answer is B. Kruskal's algorithm works by sorting all edges and adding them if they don't form a cycle, to efficiently check if two vertices are in the same component, and thus would form a cycle. We use the disjoint set union (DSU) or union find data structure with path compression and union by rank. These operations are nearly constant time. What is the maximum number of edges in a simple undirected graph with $v$ vertices? Option A, $v$. Option B, $v, $v1. Option C, $v, $v1, $2. Option D, $2 volts, $2. The correct answer is C. In a simple undirected graph, each pair of distinct vertices can have at most one edge. The number of ways to choose two vertices from $v$ is given by the combination formula $binom v2 which is $frac v v1 $2. For a directed graph, the answer would be $v v1 because the direction matters. Kruskal algorithm for finding strongly connected components (SCCs) involves how many passes of DFS? Option A, 1. Option B, 2. Option C, 3. Option D, log V. The correct answer is B. Kruskal algorithm uses two DFS passes. The first pass is on the original graph to determine the finishing times of vertices. Pushed onto a stack, the graph is then transposed. All edges reversed. The second DFS pass is performed on the transposed graph in the order of the finishing times from the stack to identify the SCCs. Which algorithm can detect the presence of a negative cycle in a graph? Option A, Dijkstra's algorithm. Option B, Prim's algorithm. Option C, Bellman-Ford algorithm. Option D, BFS. The correct answer is C. The Bellman-Ford algorithm relaxes all edges $v minus $1 times. If a further relaxation is possible on the $v$th iteration, it indicates that a path's weight can be infinitely decreased, confirming the existence of a negative cycle. Dijkstra's algorithm cannot handle negative weights and thus cannot detect negative cycles. The Ford-Fulkerson method is used to solve which type of problem? Option A, shortest path. Option B, maximum flow. Option C, minimum spanning tree. Option D, traveling salesperson. The correct answer is B. The Ford-Fulkerson method, and its implementation via Edmonds-Karp, computes the maximum flow in a flow network. It works by repeatedly finding, augmenting paths in the residual graph. Paths from source to sink where more flow can be pushed, until no such paths remain. A graph where every pair of distinct vertices is connected by a unique edge is called a Option A, bipartite graph. Option B, complete graph. Option C, connected graph. Option D, planar graph. The correct answer is B. A complete graph, denoted as $k_n$, is a simple undirected graph where every vertex is adjacent to every other vertex. In such a graph, the number of edges is exactly $v, v1, $2. A connected graph only requires a path to exist between all pairs, not a direct edge. What is the time complexity of both BFS and DFS when using an adjacency list? Option A, $O, V, $. Option B, $O, V squared, $. Option C, $O, V plus E, $. Option D, $O, V log E, $. The correct answer is C. When using an adjacency list, both algorithms visit every vertex once, $V$, and examine every edge connected to those vertices. Since each edge is examined at most twice, once for each endpoint in an undirected graph, the total time complexity is proportional to the number of vertices plus the number of edges. $O, V plus E, $. An articulation point in an undirected graph is a vertex that, if removed, Option A, reduces the number of edges to 0. Option B, increases the number of connected components. Option C, turns a DAG into a cyclic graph. Option D, forms a complete graph. The correct answer is B. Articulation points, or cut vertices, are critical nodes in a graph's connectivity. Removing such a node breaks the graph into more pieces, components, than it originally had. Finding these points is essential for network reliability analysis and can be done in $O, V plus E, $ using DFS. A graph is bipartite if and only if it does not contain a cycle of Option A, even length. Option B, odd length. Option C, length greater than 3. Option D, any length. The correct answer is B. A bipartite graph is one where vertices can be divided into two independent sets such that every edge connects a vertex from one set to the other. If a graph contains an odd cycle, it's impossible to alternate colors or sets around the cycle and return to the start with a valid coloring. Thus, no odd cycles are allowed. In a directed acyclic graph, DAG, what is the most efficient way to find the shortest path from a single source? Option A, Dijkstra's algorithm. Option B, Bellman-Ford algorithm. Option C, topological sort followed by edge relaxation. Option D, Floyd-Warshall algorithm. The correct answer is C. For DAGs, we can find the shortest path in $O, V plus E, $time by processing vertices in topological order. Since there are no cycles, once we process a vertex, we are guaranteed to have found its shortest path because no subsequent edges can circle back to it. This is faster than Dijkstra's $O, E log V, $. Handshaking lemma states that the sum of degrees of all vertices in an undirected graph is equal to Option A, the number of edges. Option B, 2 times the number of edges. Option C, the square of the number of vertices. Option D, half the number of edges. The correct answer is B. The handshaking lemma arises because every edge $U, V, $, contributes exactly 1 to the degree of vertex $U$ and exactly 1 to the degree of vertex $V$. Therefore, when you sum all degrees, every edge has been counted exactly twice. Sum deg V equals 2 E $. Which algorithm is a best first search that uses a heuristic to guide the search towards a target node? Option A, DFS. Option B, BFS. Option C, A** search. Option D, Dijkstra's algorithm. The correct answer is C. A search is an extension of Dijkstra's algorithm that uses $f n equals g n plus h n dollar, where $g n dollar is the cost from the start to node $n dollar, and $h n dollar is a heuristic estimate of the cost from $n dollar to the goal. This informed search often finds the shortest path much faster than Dijkstra's by focusing on nodes that look promising. A bridge in an undirected graph is an edge that Option A, connects two different SCCs. Option B, is part of the MST. Option C, when removed, increases the number of connected components. Option D, connects a leaf node to the rest of the tree. The correct answer is C. Similar to an articulation point, a bridge is an edge whose removal disconnects the graph, or a component of it. In a tree, every edge is a bridge. In a cycle, no edge is a bridge. Tarjan's bridge finding algorithm identifies these in $O, V plus E, $time. A tree is a connected graph with how many edges? Option A, $V. Option B, $V minus $1. Option C, $V plus $1. Option D, $2V. The correct answer is B. A key property of a tree, a connected acyclic graph, with $V vertices is that it must have exactly $V minus $1 edges. If it had fewer, it couldn't be connected. If it had more, it would necessarily contain at least one cycle. Which algorithm is used to find all pairs' shortest paths and can handle negative weights but not negative cycles? Option A, Dijkstra's. Option B, Kruskal's. Option C, Floyd-Warshall. Option D, Prim's. The correct answer is C. Floyd-Warshall is a dynamic programming algorithm that considers all possible intermediate vertices to find shortest paths between all pairs. It correctly handles negative edge weights. However, if a negative cycle exists, the shortest path is undefined. It's negative infinity, and the algorithm's diagonal values will become negative. What is the complexity of checking if an edge exists between two vertices $U and $V in an adjacency matrix? Option A, $O, $1. Option B, $O, V, $. Option C, $O, E, $. Option D, $O, log V, $. The correct answer is A. The primary advantage of an adjacency matrix is that checking for the existence of an edge $U, V, $, is a simple array lookup, matrix, U, V, This is an $O, $1 constant time operation. In an adjacency list, this check would take $O, degree, U, $, which could be $O, V, $, in the worst case. Kahn's algorithm for topological sorting uses which of the following properties of vertices? Option A, out degree. Option B, in degree. Option C, weight. Option D, color. The correct answer is B. Kahn's algorithm works by maintaining the in degree number of incoming edges for each vertex. It starts by adding all vertices with an in degree of 0. No dependencies to a queue. As vertices are removed from the queue, the in degrees of their neighbors are decremented. If a neighbor's in degree reaches 0, it is added to the queue. How many spanning trees does a complete graph $k_n$ have? Cayley's formula. Option A, $n$2. Option B, $2$n$. Option C, $n$n$2. Option D, $n$1. The correct answer is C. Cayley's formula is a classic result in graph theory stating that for a complete graph with $n$ labeled vertices, there are $n$n$2 distinct spanning trees. For example, for $n equals $3, there are $3 3 to 2 equals $3 spanning trees. What is the time complexity of the Bellman-Ford algorithm? Option A, $O, V plus E, $. Option B, $O, E, log V, $. Option C, $O, V, $. Option D, $O, V cubed, $. The correct answer is C. The Bellman-Ford algorithm relaxes all $E$ edges in the graph $V-1 times. This leads to a total time complexity of $O, V, C DOTE, $. This is slower than Dijkstra's but more robust as it handles negative weights and detects negative cycles. Can BFS be used to detect a cycle in an undirected graph? Option A, no, only DFS can. Option B, yes, if we encounter a previously visited node that is not the parent. Option C, yes, only if the graph is weighted. Option D, no, BFS is only for shortest paths. The correct answer is B. In an undirected graph, BFS can detect cycles. During traversal, if we see an adjacent node that has already been visited and is not the parent of the current node, it implies there is another path to that node, forming a cycle. Which traversal is guaranteed to find the node closest to the root in an unweighted tree? Option A, DFS. Option B, BFS. Option C, pre-order traversal. Option D, post-order traversal. The correct answer is B. BFS explores nodes level by level. Because it visits all nodes at distance $d before any nodes at distance $d plus $1. It is guaranteed to find the closest node, shortest path. In any unweighted structure, DFS might go deep into one branch and find a target much further away before ever checking nearby branches. That wraps up our 30-question deep dive into graph algorithms. Graphs are the backbone of social networks, GPS mapping, and recommendation engines. So mastering these concepts is a huge step for your career. If you found these explanations helpful, hit the like button and subscribe for more DSA deep dives. For the full interactive practice experience and more in-depth content, check out the link in the description below.